It's my pleasure to introduce Professor Abhijeet Ghosh. He's a professor in Imperial College London. He's also a senior staff research scientist in Google Research, and he was CTO and co-founder of Logarithmic. And he has several awards like Royal Wolfson Award, Merit Award, EPSRC Early Career, and so on, Google Research Faculty Award, and so on. He'll be talking about computational imaging for realistic facial appearances. Thank you.
Thank you so much for the kind introduction, and it's a pleasure to be here at the BMVA Symposium. It's my first time to attend one of these symposiums, so I'm really pleased to see the quality of the talks and all the speakers. It's amazing to be here. So yeah, me being at Google is a relatively new development, so I'm just also myself adjusting to that reality. But for the purposes of this talk, everything that I'm going to be presenting is stuff that has been done at Imperial or the spin-out startup that came out of Imperial, Logarithmic, that when I just alluded to. So the title of this talk is Computational Imaging for Realistic Appearance Capture. And for the most part, it's a dinosaur talk in modern terms because it basically is the antithesis of modern AI. It just mostly avoids AI as much as possible. So bear with me, and hopefully this is still interesting to many of you. So what are we trying to do? For the most part, in my work, I want to do imaging for realistic rendering, but not always for rendering, but at least for the most part for rendering. And we want to go from a photograph like this of a person, and we want to do measurement-based appearance modeling such that we can then arrive at high-quality geometry and appearance representations that drive a realistic rendering of that subject. And in order to do that, to go from input to output, we have to usually solve an inverse problem. An inverse problem can be under constraints, so we want to do not regular photography, but computational photography to provide as much information as possible to arrive at direct estimates of these appearance properties that we care about, for the most part, avoiding as much as under constrained optimization as possible. Not always, but as much as possible. So my general research up until now has been in this space on imaging for realistic appearance modeling, not just for human faces, but also for objects and materials. And by and large, my lab has taken this philosophy of using computational illumination or photography, or sometimes combination of the two, to arrive as much as possible with the direct estimates of physical parameters of materials that we see in the real world. And this talk is going to present things that we focus on: different illumination basis design, different modalities of illumination, whether it's playing with the polarization of it or the spectra of it, and essentially, again, try to arrive at practical capture systems. So we want to minimize, the number of measurements and the hardware required to make those measurements as much as possible as we go along this journey of this talk. So this is just to set the scene. This work is a bit interdisciplinary in the sense that it kind of sits at the intersection of these different things that you see on the slides. There's a little bit of machine learning that's starting to come into this. Obviously, with times I have to modernize, otherwise I'll be a dinosaur, as I mentioned. So this talk, we're going to talk about biophysical facial appearance capture and modeling. First part of the talk is going to focus on high quality facial capture for realistic rendering, and the second part of the talk is going to talk more about biophysical facial appearance, and that has applications in rendering, but can have applications beyond rendering in skin imaging, for instance. So the story starts with light stages, and this was my first job after my PhD, where I joined Paul Debevic's computer graphics laboratory at the University of Southern California. And then they were, at that time, just developing the technique called polarization and applying it to the light stages. And the technique that they developed at the time was called polarization spherical gradient illumination. But fundamentally, what happens with polarization is that it essentially limits the wave property of light, which is its electrical field oscillation, to be in a fixed plane, which means when light is polarized and it hits a dielectric surface like human skin, the specular reflection reflects preserving the original polarization, so it remains what is called parallel polarized with the input. And that's because it's just a single bounce. Whereas the diffuse reflection that we see in human skin or any translucent material is the result of subsurface scattering within it, which when it comes back out has scrambled its original polarization, so it's now essentially randomly polarized. So why does that help is that if you then take a photograph with a camera which is cross-polarized with respect to the light's polarization, you don't see any of the shine because that is this image basically blocking out the original polarization. Whereas if you have the camera's polarizer oriented with the light's polarization, then you see both the shine and half of the diffuse reflection. Basically, both images will have half the diffuse because essentially the projection of random polarization to a specific polarization essentially is a sinusoid that sums to half. So long story short, you will do A minus B to extract what is the pure specular reflection, in this case, the shine that sits on your skin, which is the result of the top oily layer of your skin. You can do that for any lighting condition, and in this case, they specifically designed polarized spherical gradients where you create not just constant light from all directions in the light stage, but linear gradients of X, Y, and Z directions variation, which then helps you get very high quality diffuse and specular shading information, which allows you to extract high quality photometric normals. And interestingly, diffuse normals have less detail because of subsurface scattering blurring, which is also, by the way, channel-wise independent, which means red has the most scattering in skin and has hence the softest normal maps, whereas the blue has more detail, and then the specular channel has the most detail, showing every single skin pore level detail. So this was quite revolutionary back in the day, and it produced very nice renderings. In this case, by the way, this is actress Emily O'Brien, who we scanned with this technology for the first version of the Digital Emily project. But there was a big problem, and the problem is that all of the lights on the light stage were polarized such that the frontal camera would achieve this nice cross and parallel polarization, which means you could only do a single stereo pair frontal face scan. And obviously that's not desirable for digital humans. We want to do high quality multi-view scanning. So this is when basically I worked on the problem, and the solution that we came up with is to essentially create a different way of polarization multiplexing where you don't rotate the polarizer in front of the camera. In fact, you let it stay fixed. Instead, you do polarization multiplexing on the light stage itself. And the natural solution, which in hindsight looks obvious, is that you go with what is called the lines of latitudes and lines of longitudes of horizontal, which is the red lines, and vertical, which is the blue lines of polarization. But it's not as simple. I had to do a lot of analysis to make this prove that this is the optimal way to do it. This only works when you have a fixed vertical polarizer on your cameras, and it doesn't work if you have a horizontal one. Here's a little bit of analysis where we compared this to various combinations, and including a completely obvious possibility, which is circular polarization. It turns out even circular will have issues beyond the Brewster angle because circular polarization flips in its chirality, so you don't get as nice a clean image as you will get with this specific combination, which the proof is in the details, basically. So the setting is such: you have vertically symmetric polarization field. All lights, all cameras now can be placed multi-view around the light stage. As long as they are relatively around the equator of the light stage, this produces a good result. And then sequentially, you will basically either switch on the horizontal banks of polarization on the light stage, and you'll get a nice, clean, cross-polarized image. Then you'll switch on the vertical banks of lights on the light stage, and get a nice parallel polarized image. Then in software, you can just do A minus B, and you can do that for any lighting conditions, so not just the full-on, but also the gradients, and you'll get multi-view, high-quality, diffuse specular separated photometric normals and albedo maps, which then, back in this SIGGRAPH Asia paper, we applied to 3D facial reconstruction and rendering. So this was a result that was produced with a very small light stage with just 5 cameras, which is why I literally have 5 cameras in that diagram. But of course, modern systems extend this to potentially lots of cameras and lots of lights on a light stage. This method turned out to be the basis of light stage scanning used extensively at USC for Hollywood, and then also licensed out to various scanning companies that Hollywood then uses. And technology contributed to an Academy Award for some of my colleagues at USC in 2019. My personal favorite was that the SIGGRAPH Asia paper came out in 2011, and by early 2012, we were scanning Tom Cruise with it. So I was like, yeah, mission accomplished. But since then, of course, I haven't been part of the USC ICT graphics lab. I moved to Imperial, and then a decade of research followed where I ignored facial capture because obviously I didn't have a light stage. But more recently, I spun out a company from Imperial called Lumirhythmic, and what we wanted to do was essentially come up with a new form factor to do high quality digitization in a much more practical form factor. So we built two different setups. They both fundamentally work on the principle that you have a desktop infrastructure with some screens on it, and some bunch of cameras can sit between those screens, and the screens essentially act as your light stage. And the cameras that you can fit within them, which have to be small in their form factor, should be sufficient to then, in the modern days, be able to produce high quality reconstruction. So on the left, you have iPads. And in this particular example, we used iPhones because they kind of felt nice and fitting with iPads. But other settings, we've also replaced them with mirrorless digital SLR cameras as well. But the point is that you just do small form factor camera and screens, and you have a small light stage. So with that setup, we can do digitization of this kind of quality these days, where you can achieve very high quality realistic rendering with this kind of capture. But there are certain challenges you have to overcome. Before we get to the challenges, let's talk. Let me just show you a little video of the scanning process. So what you see is some funky, colorful lighting that you saw on the screens, and it's a two-shot method. And that was enough to then produce the scan of the subject to produce this rendering that you see. So now we've gone from white lighting, which was originally on the light stage, to a colorful lighting. And turns out we also go away from polarization. And one of the reasons to go away from polarization is, of course, that the screens don't produce that much light. So if you then use polarization, you're going to kill half of that light again, and hence give yourselves low signal to noise ratio. So instead, in this particular setting, we're using binary illumination conditions, which means half the screen is on and half of it is off. And then we multiplex that in the X and the Y direction. Now, given the extent of the screens around the face, you could do one in the Z direction, but it turns out you don't actually need to do it, just because of the extent of the screen. The X and the reverse X fundamentally act as roughly orthonormal bases to each other within the setup, where the orthonormal basis is kind of 45-degree rotated off the regular X-Z axis, so to speak. So that means just X and Y conditions are sufficient to encode X, Y, and Z information of a photometric normal with this kind of illumination coverage. So what we do is we illuminate the subject with the X and Y, and of course, if you add up any of those two conditions, it also produces a full-on. For surface normal recovery, then we just compute an SVD, and the principal components of the SVD then point to these X, Y, and Z directions. And that's our high-quality photometric normal with just that kind of illumination. Now, we want to do diffuse specular separation, but now we don't want to use polarization, so we need to do something else. So the solution we here use is what is known from color space theory, dichromatic reflectance, where specular reflection is white and skin reflection is colors. That essentially you have the same amount of specular sitting in all color channels, but a different amount of diffuse in different channels. And in human skin, red channels is the dominant scattering and brightest component, and blue is the least dominant, most absorptive component. So if you did red minus blue, then you'll get a subsurface scattering component that does not have specular, because specular in both will subtract. So that's one way of doing channel-wise specular separation. And of course, if you did this for all of the lighting conditions that we captured, then you can send that through the SVD and you'll get a blurrier photometric normal, which we then call the diffuse normal. This diffuse is not the same as what you would get with polarization, but it's In fact, it's a bit softer because I call it a subsurface diffuse, but it serves the purpose of giving you a nice shading normal that encodes subsurface scattering. For diffuse specular separation and actually isolating specular, we exploit the binariness of the illumination. And so this nicely sets up a linear system where the shading on each pixel in each of those two photographs can be modeled as either you're in an X condition or you're in its X prime condition, which is its complement condition, where you're either shaded with only the diffuse component if you're on the dark side of the gradient of the binary condition, or you're shaded with the diffuse plus the specular if you're on the bright side of the condition. So that just sets up that linear system, which then turns out you can solve and get your diffuse and specular separation. In practice, of course, it's a little bit more complicated. We have two pairs, X and Y. We solve this linear system individually for each of those pairs. They give slightly different results. And then to get essentially the final result, we kind of do an average of the two results that we get. And then that means that we can now take our original photograph, which has diffuse plus specular, and subtract the specular image out of it, and then that isolates our pure diffuse albedo. Now again, this is a color space separation, which assumes purely white specular reflection, which is more true on skin and less true on any clothing that you might be wearing, particularly if it is white or pastel in its color. So you will notice that the diffuse specular separation makes sense more on the skin and less on the clothing. But it's sufficient for the purpose that we were targeting this for. All right. Now, that was a 4-pattern lighting condition. How can we squeeze it further? Well, it turns out you can do color multiplexing of your lighting conditions and collapse the 4 conditions that I showed you to just 2 conditions, which are complementary in that they add up to white light. Now, in principle, makes sense. In practice, there is a problem, and the problem is that we are using screen illumination where essentially the primaries of the screen, red, green, and blue, have this kind of spectral power distribution. And the dashed lines that you see are the sensitivity of the color camera that we are using. Blue and green are well separated, but our problem was that green and red are kind of overlapping due to the spectral sensitivities of the color channels, which means there is spectral crosstalk between these two color channels, which means if we just naively mix the lighting conditions, we could have a problem. Turns out just because of our design of binary conditions not requiring 3 different binary conditions, but only 2 different binary conditions, we can spatially separate green and blue, red lighting conditions at a time when we illuminate, which means there is no spatial overlap between red and green, while allowing an overlap of blue with either of the 2 because they are well spectrally separated, which means this results in these 2 lighting conditions, which then add up to white light, which then add up to the 2 conditions that I just showed you on screen, which then allows you to do all of that math that worked with white light. But now you just have to be very, very specific which channel operates on what data in which way, and you still get everything you wanted. So now this is a 2-shot method with color space separation of diffuse and specular, and photometric separation of specular normals and diffuse normals, which produce hopefully high quality rendering. By the way, here's a comparison of our color space diffuse on the right column with polarization based diffuse in the center. So again, not exactly the same, but qualitatively similar enough that it's quite acceptable in practice to achieve this, which again works better for skin than for clothing because of the assumptions we make. Here's some, I would argue, relatively high quality scans that we got with, at the time, just phone cameras and iPads. You can get even higher resolution with higher resolution digital SLR cameras, obviously. And of course, the form factor is nice. It just sits on a desk. It can be any screens. So regular computer monitors also suffice for this purpose. I'm going to skip this result because I already just showed you. Now, the same thing also extends to dynamic capture, but the hardware required for this is a bit more complex. So it turns out in this case, we couldn't use the iPads anymore. We switched to computer monitors. And the reason for that is that depending on what graphics card you have on your workstation, certain beefier ones can synchronize 4 monitors at video rates. So with that synchronization, if we drive these monitors at 60 FPS in synchronization, then it turns out that you can capture a subject effectively at 30 FPS because you have a two-pattern lighting condition. In practice, it turns out you can actually extract 60 FPS because you can do complement, binary and its complement, one solve, and then the complement and binary as the next frame solves. So every adjacent pair will give you one solve. So even though you are using 2 frames to solve for 1 frame, because you have continuous frames, you can keep solving. So you effectively don't lose out on the frame rate if you do this right. The bigger challenge, of course, is to have a camera synchronized with the screens. And in this case, we used a machine vision camera, but if you had multiple of them, things would get complicated. You would need capture cards and synchronization hardware that has to go into your workstation. It's more complicated, but doable. So here is a regular video rate capture of someone just doing a few facial expressions. Per frame, we are solving for their diffuse and specular albedo and photometric normal, and the relighting that you can get you can see on the right. I'll just play the video again. You will notice that the image is a lot noisier than before. This is because at video rates, there isn't really that much light a screen is producing, but you can still hopefully get quite high quality data with a setup like this. So we were quite pleased when we got this. This was published at ECCV in 2022. So it's basically been a decade worth of work to go from that light stage design with its high quality polarization based separation to this color space alternative way of doing it on a smaller form factor. So this is us squeezing things out to in minimalistic possible in both capture setup and number of lighting conditions to directly extract stuff without using deep learning. Obviously, there have been lots of papers out there that would be able to just predict everything from just a single image under natural lighting conditions with deep learning. But this is trying to actually measure what's really real there in the data. Any questions before I move forward? Yeah.
One question. So in your surface normal, if you consider these 3 RGB values as a vector, the problem is that just especially that USC paper, that when the blue channel has a different values, it can push the red and green channel to just move that vector. So because just imagine if the values are 128, 128, 128, but if you consider 120, 155, 155, 155, they are just a vector, will give us same angle in your Cartesian coordination system. But one of them, the blue channel, would just can be happen because of some shadows from around the eye or just from the nose.
Yeah, I see what you're talking about. Yeah, so definitely bias in the data set. We are currently with the binary lighting condition. We are relying on the fact that the diffuse integration of a binary condition is creating the gradient for us through shading without us having to explicitly create the gradient on the light stage. So that is an underlying assumption, and the other assumption is that there is no spectral crosstalk between red, green, and blue. That means we are achieving clean signal. This is why we had to do that spatial separation of red and green, because there was spectral crosstalk between red and green. But I don't think blue, in our case, was affected by any of those. What it can be affected by is lower signal quality, because blue reflectance is just lower in human skin than red and green. So that may be more of a factor than any bias due to spectral crosstalk.
So don't you think that can be the reason that in your surface normal and the specular you can see, even though the skin is the same, but you can see more bluish in some of the region in the surface normal, or you can see one more specular points on the specular albedo.
You're talking about this?
I talk about the specular albedo and surface normal and both of them.
So this is a color space separation. It doesn't work as well as polarization-based separation. So yeah, that's a good point. With color space separation, effectively what you're taking is a mixed color of white and color and moving anything that is whitish to specular and what is non-whitish to diffuse. And that's one of the big limitations of color space theory. So higher the contrast, the more correct the separation. For lighter the skin color of a subject, so essentially white people, there is more diffuse pollution in the specular because essentially the color space theory just cannot distinguish white diffuse and white specular at that point. It's a very good question. All right. So until now, I talked about facial capture mostly for the purpose of obtaining albedo maps and photometric normal maps for regular realistic rendering. I'm switching gears now a little bit to cover some of the work we've done on biophysical skin appearance capture. And that also has its application in realistic rendering for subjects, but I'll also talk about some just regular skin imaging applications. So the first project we worked on this was on practical spectral imaging to essentially achieve estimations of subsurface spatially varying chromophores in skin that essentially give rise to the appearance of skin color. This was work led by my PhD student Yulia Gitlina at the time, in collaboration with my postdoc Daljit Dhillon at the time. He's now a faculty member at Clemson University, and my longtime collaborator and former PhD student, Claudio Guanera, who's now an academic at the University of York. So the idea here is that we should now stop looking at diffuse color as diffuse texture, as we normally do in computer graphics, but start to actually recognize that this is the cumulative result of subsurface absorption and subsurface scattering due to chromophores within human skin. And there have been models that have been developed in computer graphics that have been borrowed, obviously, from original work in tissue optics literature that says that there are several layers of human skin. We, in computer graphics, for the most part, will simplify it to a two-layer model with an epidermis, which has melanin, which absorbs light and essentially protects most of us from, hopefully, things like skin cancer. But different people and different races have different amounts of melanin, which is why my skin color looks different from yours. And below that, there is the dermis, which primarily has hemoglobin, which is another spectral absorber and essentially reacts to blood in human skin, which is why it gives rise to the reddish appearance underneath the skin. Before we did this work, there's been lots of work in computer graphics and tissue optics, and they all worked on different aspects of it. So there were some very high quality, complex, sophisticated spectral subsurface scattering models developed in the literature that we looked at. The problem was that there was almost no way to measure the parameters for these models for a whole human face. On the other side, there's works by Donner et al. And Jimenez et al. On measurements of human skin to then fit to some spectral BSSRDF models. The measurements were either done only for small skin patches with dense multispectral imaging, or simplified for practical capture to just a two-dimensional model where you see a two-dimensional lookup table here with one axis being melanin and the other axis being hemoglobin. What we wanted to do is kind of bridge the gap between the two. We want to measure a full face. We want to measure as much as possible in multispectral fashion. And we want to kind of marry the measurement to the more sophisticated biophysical appearance models. And we don't want it to take ages because the subject cannot stay still. So what can we do? So in my lab, we built a multispectral light stage. This was work done by PhD student Christos Kampouris, where we had, for every lighting node, two different types of LEDs, one narrowband RGB LED and another broadband white LED, except that these white LEDs themselves have three different types of spectra, from cool white, 5700 Kelvin, to warm white, 2700 Kelvin. And that gives us a relatively good control over the spectral power distribution of light that we can emanate from this light stage onto a subject. So we use that, in this case, to try and reason about the spectral constituents of human skin. And of course, we use polarization and cross-polarization to block out all specular reflection. And then we want to do the minimal possible measurements and the best possible measurements to essentially reason about these two types of chromophores that we care about in skin. And what we then, after a bit of work, settled on is one very nice broadband white lighting condition, which is actually a metamer for D65 daylight spectrum, which is a very good lighting condition, irrespective of whatever you use it for measuring human faces. And this gives us a very good measurement of both melanin and hemoglobin, because it measures both epidermal and dermal response. And on top of that, we add one more condition, which is a narrow band. And in this case, it turns out this blue lighting condition that we have on our light stage is very, very good for isolating, especially the epidermal melanin response. Beyond reducing measurements to these two complementary lighting conditions, we also search the space of parameters that we need to actually model to achieve high quality measurement. And it turns out just a two-dimensional model of melanin concentration, hemoglobin concentration did not have wide enough a gamut to properly model all of the different things we see in regular human skin. So we found that we had to add spatial variation to the melanin blend type being a blend between two different types of melanin found in human skin, eumelanin and phosphomelananin. It's actually also present in human hair, by the way. And the hemoglobin concentration, we also had to vary that in both the epidermis and the dermis. So these are essentially additional parameters in your model, going from a two-dimensional model to essentially a four-dimensional model. It creates a very subtle difference, but enough of a difference that we think it was worth it. So with a two-dimensional model, you miss some of the rosiness of the cheeks and the nose on this subject that are then better fit with this four-dimensional variation in the model. So this is like searching for the optimal model complexity. And then once you have it, and if you've actually extracted the parameters from your measurements, then these four parameters can predict a spectral response of human skin under different input spectral lighting conditions. So what you're noticing here is that you see a lot of skin texture under white light, broadband white light. This is the D65 metamer. But then appearance of skin changes quite drastically as you go from cold white to neutral white to warm white lighting conditions, where in warmer spectrums, you almost start to lose the appearance of skin texture. This sort of variation would not be possible if you were rendering with an RGB diffuse albedo, because you would just take that albedo and multiply it with some scalar color, which means it'll just suppress the texture, but it'll not make it completely go away. But in reality, under spectral lighting, things actually go away or they appear. It's much more visible in this scenario, where now you're using narrowband RGB illumination, and under green and blue, you will see strong texture of the epidermis, which completely disappears under red light, because red light penetrates deeper into the skin, and you don't see that in the epidermis at all. You're just seeing dermal scattering, basically. And so this behavior is only possible when you're rendering with a biophysical skin appearance model. All right, so how do we achieve this hopefully optimal measurement? We have these 6 LEDs on our light stage, and each of those LEDs has a spectral power distribution plotted on this graph. We looked at the literature, and we actually found that there were studies in human facial perception for expression studies and health analysis that empirically found that D65 daylight spectrum was really good, or rather optimal, ideal for this purpose. So we tried to reason why that might be. Well, it turns out if you look at the spectral signature of human skin reflectance, it is dominantly red. Brightness is high in red, less in green, and least in blue. So there's basically a slope going from blue to red. If you look at the spectral signature of D65 daylight spectrum, it's kind of the opposite. It's dominantly in blue because of the blue sky and kind of tapers down towards red. So now if you illuminate that skin patch with this illumination, essentially it's an integral of these two dot product, if you want to think about it, then essentially what you get is a more flatter spectrum of the reflectance response. So we think it's because bluish light counters reddish skin that bluish white light is the desired white light. So this tells us that whenever possible, produce white illuminance if you can that mimic broadband daylight spectrum as much as possible. Now, it may or may not be possible, but depending on what kind of illuminance you're using. And in fact, it's usually not possible with LEDs because LEDs have a specific thing called a spectral gap. So most white LEDs have a gap around the cyan band where they are not exciting the phosphors. So having a multispectral setup like this actually helps bridge that. So what we did is we essentially looked into an optimization problem where a color chart lit with some linear combination of those 6 LEDs will produce a photograph that is essentially indistinguishable to the human eye to a photograph of the same color chart under ideal D65 light. And that's why we call it a metamer, because it's not physically the same light, but perceptually it has the same effect. And in this case, this is the shape that our LEDs, 6 LEDs, jointly were able to produce. They did not completely bridge that cyan gap, but they minimized its effect in practice, that this turned out to be a nice proxy for the ideal D65 illumination. All right, so now we've got the nice white light we want to produce with the light stage. Next comes the narrowband illumination. Well, it turns out in literature we looked that 485 nanometers is the ideal narrowband illumination wavelength which excites melanin in human skin. This is work from Priest and Claridge. I highly recommend looking up their works in tissue optics. They were very, very educational for me, at least. The problem is that actually if you illuminate someone with just the blue LEDs of the light stage. Oh, by the way, first the good news. The good news is that we actually had a blue LED on our light stage whose peak was at 480 nanometers. So we were like, yeah, because it's almost 485. Now comes the bad news. The bad news is that if you produce illumination directly with that blue light and image with a color camera, then some of that quantity of light and its information goes outside the sRGB spectrum that your color camera can measure. Which means that even though we have the ideal lighting condition with a regular color camera, we can't measure it appropriately. So the solution turns out quite counterintuitively is to mix some white light with that blue light, making the blue light not super narrow band, but actually a little bit broadband. But what it does is it actually moves the dot from outside the triangle, which is your sRGB spectrum, to back inside your sRGB spectrum. And now you can do a computational technique afterwards to extract the ideal quantity that you were looking for. So here is a direct measurement with blue light. And if you isolate the blue channel on the color camera, you will notice that that's the details you're getting. You are seeing the melanin texture that you were hoping to see, but you might notice even on these screens that it's slightly blurry. Instead, if you mix a little bit of white light and then illuminate with this bluish white light, then there's something called a chromatic adaptation transform and some computation where given that measurement and that measurement, you can computationally extract a narrowband image, which we call synthetic blue in the paper, which turns out to be a higher quality narrowband illumination image than if you directly measured it. So on the left is a direct measurement, which is slightly blurry. On the right, I hope you can see, is a sharper image that we extract with this chromatic adaptation transform. So the point I'm trying to make here is we need to very, very carefully analyze the limitations of our hardware and our cameras and our illuminants and play all kinds of games we can play computationally to achieve the best of result. In the previous case, we separated green and red so that we have less crosstalk. Here we mix white with blue so that we can actually get a better reconstruction in software than we can get with direct photography. So these are just some tricks we can play with measurements. Of course, with modern world, we have to deal with neural networks. Otherwise, maybe reviewers don't like it. But in this case, we actually had a practical purpose. The way we are actually fitting the data is we are looking up a high-dimensional lookup table, a 4-dimensional lookup table to be precise, that takes your RGB measurements under these different lighting conditions and searches for the best parameters. Well, a neural network can do that job quite fast compared to a brute force lookup table search. So this was work by Claudio Guarnera. He designed a cascading network architecture that first predicts parameters that are more directly measured by our imaging system, like melanin concentration, and then that feeds into subsequent networks that take each of the predicted inputs and the original measured inputs through it, eventually producing 4 parameters as the cumulative output of all of these cascading architecture. And then this goes through another fully connected network to finally produce the input RGB albedo that we want this to predict. So this whole system is jointly trained, and it achieves much faster reconstruction of the parameters and then the full color reconstructions than would be possible with lookup table search. So something that was taking 40 minutes on a 2K resolution was down to a few seconds, basically. The other benefit, of course, with neural networks is that the training data was discrete lookup table values, but the prediction with neural network is a continuous value and also suppresses noise. One downside, of course, is that because we are training on RGB input and RGB output, you need to train a different neural network for every different type of lighting condition you want to visualize the face under. So in this case, we had to train a different neural network to predict under D65 illumination versus under warm white illumination. And that is one of the limitations of an RGB-specific neural network. But hold on to that. We will fix that shortly. Now, of course, we did all of this. Why should we bother doing this? Well, in computer graphics, we want to create nice images. So, of course, we took the PBRT ray tracer and we modified its photon mapping implementation to, am I out of time? Oh, couple of more minutes. Okay, let me skip that. It's possible to modify PBRT to do spectral rendering. And so the same chromophores are predicting the appearance under all of these different lighting conditions. So subsequently, we've expanded the number of parameters and again switched from the light stage to computer screens. And it turns out we can now do hyperspectral prediction. So even though we make measurements under visible light emitted by screens, we can predict values of how the skin might appear in the UV range or in the near infrared range. It turns out we can do that quite accurately. I'm going to skip the detail. One thing is that we've now expanded the neural network to directly predict spectral reflectance response, which means the same network can predict predictions under different illumination spectrum. We don't need to train a different neural network for every desired illumination spectrum. Here's some validation. The model prediction is on the right. The actual photograph of the subject under infrared and ultraviolet is on the left. So again, visible light measurement, but hyperspectral prediction. And of course, if you have chromophores, you can do chromophore-based editing of melanin and hemoglobin to produce different effects. One last thing I will want to show you is that with the same kind of RGB illumination, we can now go beyond rendering-related tasks, but do actual skin imaging. So it turns out with RGB light, in our more recent work, this is work done with PhD student Emily Nogue, we've essentially measured some weak elastin fluorescence in skin and also extracted things like blood volume fraction, blood oxygen rate. So these are weak signals, but just stretching the limits of what is possible. Elastin is essentially a protein in the dermis which essentially provides you the stretchability and health of your skin. It achieves the highest concentration as skin matures and then degrades with old age, which is why old age develops wrinkles and loses elasticity. It has what is known as a fluorescence as an inherent property, where fluorescence is light being absorbed at a high energy state, lower wavelength, and emitted at a lower energy state, which is a longer wavelength. Now, in tissue optics literature, you would normally be imaging things in the UV range to visualize this fluorescence in the visible range. But with our screen illumination, it just turns out we measure the tail end of the emission spectra and then the tail end of the absorption spectra and then the re-emission spectra. So it's a very weak signal, which is why you see a noisy image. But it's quite interesting how well we are able to extract that fact that lips have high elastin, nose has high elastin, ears have high concentrations of elastin compared to the rest of the skin. And we do that by essentially doing simple mathematics of, again, extracting different information from different color channels. This is what you can do with just looking at the green and the blue photographs under green and blue light. Similar things you can do on the red and green and blue, some simple mathematics which I don't have time for, but you can extract things like blood volume fraction, which is the concentration of oxygenated blood in the epidermal or near papillary dermis of skin on the left, and deoxygenated blood on the right, which is mostly in the veins in your skin. So again, this is in tissue optics, you would use hyperspectral imaging to go deeper into skin. With RGB imaging, this is kind of the limit of what we can push, but point is that we are now still able to extract more information than previously possible with just simple setups. So unfortunately, I don't have the time to go into details, but I think I'll just wrap this up and say that we've gone from the light stage to a practical screen illumination setup for high quality facial capture and for biophysical skin imaging. And I hope that is a good story for you to take home. Thank you very much.
Thank you for the nice talk and questions. So just a small question I had, like uh, with all the fascinating things, could we push this even further with coded exposure and flutter shutter and
Yeah,
those kind of
I've thought about those sort of things, absolutely. I mean, with coded and Flutter Shutter things, you're trying to solve for things like movement and blur.
motion blur and
Here, I feel like we're looking at maybe going beyond the spectrum of white light or just light into the, like you could do things with going outside the electromagnetic spectrum and play around with different wave fronts and different sorts of sensors, and maybe that's kind of where things are. One possibility is combining like audio signals with imaging signals, right? Because essentially that's the basis of ultrasound, right?
yeah. Thank you. Yeah, thanks.
Thank you so much.